Dear students, now we are going to an important theorem. The theorem states that if theta be a complex number, theta represents in C. The theta be a complex number which satisfies a monic polynomial. Theta satisfies a monic polynomial equation whose coefficients are algebraic integers. Coefficients are algebraic integers. We know what is an algebraic integer. Then theta is an algebraic integer. For any complex number theta, which satisfies a monic polynomial equation whose coefficients are algebraic integers, then theta is an algebraic integer. Come to the proof. Since theta satisfies a monic polynomial equation, that is theta power n plus a1 theta power n minus 1, an minus 1 theta to the power n minus 1 plus an minus 2 theta to the power n minus 2 plus etc. plus a1 theta plus a0 equals 0. So this is the monic polynomial equation which is satisfied by theta, where each ai are, what is ai? Here ai are integers. A are algebraic integers. So means A fall in B. What is B? In previous class we stated that this B is nothing but the set of algebraic integers. Okay. So theta satisfies this monic polynomial equation. All of its coefficients A are algebraic integers. Then this generates, we know that this generates a subring K of B. This generates a subring K of this B. Okay. But we know that then we proved a lemma, that is a complex number theta is an algebraic integer if and only if the additive group generated by all powers, means 1 theta square etc. to theta power n minus, all the powers 1 theta square etc. is finitely generated. So by that lemma, all powers of theta which lie inside, all powers of theta lies inside a K submodule of C, finitely generated K submodule of C. Okay. But we know that we prove a theorem, that is the set of algebraic integers form a subring of the field of algebraic integers. Means set of algebraic integers being a subring of the field of algebraic integers. This is we already proved. In last class we proved this theorem, that is a set of algebraic integers is a subring of algebraic field. Okay. So field of algebraic integers, set of algebraic integers be a subring of algebraic field, means field of algebraic integers. So clearly, according to this argument, each ai and all the powers of theta lies inside a finitely generated additive group gamma I with the integers or with the generators bij, where j ranges from 1 to ni. That means the K submodule, this K submodule lies inside a additive group which is finitely generated and which is generated by the elements b1 j1, b2 j2, etc. bn minus 1, jn minus 1, bn minus 1 j as bn minus 1 jn minus 1 theta power k. That is be a finitely set term. So k is also an additive group. This k is also a finitely generated additive group. That means the k submodule finitely generated as an additive group. Hence theta is an algebraic integer by the previous theorem. Agree? Okay. Now let us go to another theorem. So the statement of the theorem is an algebraic number is an algebraic integer. Come to this theorem or lemma. There's a lemma. Lemma. The algebraic integer is an algebraic number. The algebraic integer is an algebraic number if and only if the minimal polynomial over Q. The minimal polynomial over Q. Q means set of rationals. Has coefficients in such. Has coefficients in such. Set means set of integers. So that's an interesting research. The algebraic integer is an algebraic number if and only if the minimal polynomial over Q has coefficients in such. So the proof is, let P be a minimal polynomial. Let P be a minimal polynomial of alpha over Q. Let P be a minimal polynomial of alpha over Q. Assume P is monic. Assume P be monic and irreducible. Assume P is monic and irreducible in Q of T. Okay, P be a minimal polynomial of alpha over Q, and we assume P is monic and irreducible over or in Q of T. Now, if P fall in set T, means if P fall in set of T, then what is alpha? Clearly, alpha is an algebraic integer. So the algebraic integer is an algebraic number is an algebraic the algebraic number. The algebraic number is an algebraic integer if and only if, that is the theorem. So there's a mistake in theorem. The theorem states that the algebraic number is an algebraic integer if and only if the minimal polynomial over Q has coefficient in such. So let P be the minimal polynomial of Q or minimal polynomial of alpha over Q. P be a minimal polynomial of alpha over Q. So without loss of generality, we can assume that P is monic and irreducible in Q of T. If this P fall in set T, then clearly this P is an algebraic integer. P of set T, so then alpha is an algebraic integer. Okay. If P be a minimal polynomial of alpha, where P is monic and irreducible, if P fall in set T, then clearly this alpha is an algebraic integer. So the first inclusion is finished. What about the reverse inclusion? Reversely assume that alpha is an algebraic integer. Let alpha be an algebraic integer. Let alpha be an algebraic integer. Since alpha be an algebraic integer, then there exists a polynomial Q. There is a polynomial Q presents in where? Q presents in set T. Okay. Q presents in set T, where Q is a monic polynomial with a Q of alpha equals 0. When alpha is an algebraic integer, then there exists a monic polynomial Q fall in set of T. Q is monic. This is a monic polynomial. Monic polynomial in set T with a Q of alpha equals 0. With a Q of alpha equals 0, and what is P? Then and P divides Q. Where P be a minimal polynomial of alpha over Q. What is P? P be a minimal polynomial. That alpha is an algebraic integer, means there exists a monic polynomial q of t in set t with the q of alpha equals 0, and let p be a monic polynomial, so minimal polynomial of alpha over q, then clearly p divides q. By Gauss lemma, then there is an important lemma which is a non-lemma which is known as Gauss lemma, well-known result. Let P fall in set T. P fall in set T. Suppose P equals G into H, means G of T into H of T. P equals G into H, where G of T and H of T are fall in Q of T. G and H fall in Q of T. Then there exists a lambda. There exists a rational number lambda such that lambda fall in Q, such that this lambda into G and lambda in power minus 1, lambda inverse into H, also fall in set. So this is Gauss lemma. P fall in set T means P be a polynomial with integer coefficients, and if P can be expressed as the product of two polynomials having a rational coefficients, that is P equals G of T into H of T, then there exists a rational number lambda such that this lambda into G and lambda inverse into H are also present in the set. It means lambda G and lambda inverse H having integer coefficients. Okay, so this is Gauss lemma. So in the light of that argument, when alpha is an algebraic integer, then there exists Q fall in set T with a Q of alpha equals 0, and P be a minimal polynomial of alpha, P divides Q, where Q be a monic polynomial. Okay, but we know that according to this Gauss lemma, this P fall in set T. Why? P divides Q. P divides Q means Q equals some, what is Q? Q equals some lambda into P. Okay, so where lambda presents in Q. Well, for some rational multiple lambda P lies in, means Q equals lambda P. So when P equals G of H, G of T and H of T is in Q of T, then lambda G fall in where? Set. So for some rational multiple lambda P which lies in where? Which lies in set T. So Q equals lambda P means so clearly this P fallen by this Gauss lemma, this P fall in set. Since P and Q are monic, what is this lambda? This lambda equals 1. Since P and Q are monic, lambda equals 1. So here it is P divides Q means P equals Q. Okay, P equals Q. So that means when the minimal polynomial over Q, the minimal polynomial Q be the minimal polynomial, so P be the minimal polynomial of alpha over Q, it is nothing but a Q, but a Q is an algebraic integer. Q fall in set T, therefore this minimal polynomial over Q has coefficient in set. Okay, this is an important theorem. That is, if every algebraic number is an algebraic integer, if and only if the minimal polynomial of over Q has coefficients in such. So its first part is immediate. When P is a minimal polynomial for alpha over Q, then assume P is monic and which is irreducible in Q of T. If P fall in set T, then this is finished. Alpha is an algebraic integer. Reversely, suppose alpha is an algebraic integer, then by the definition of algebraic integer, we say that there exists a non-zero polynomial, monic polynomial, Q fall in set T with the Q of alpha equals 0. As well as P is a minimal polynomial of alpha over Q, surely this P divides Q. But by Gauss lemma states that when P is a polynomial having integer coefficients, and if it can be expressed as the product of two polynomials with the rational coefficients, then there exists a rational number lambda with this lambda G and lambda inverse H are again the polynomials having integer coefficients. So here P divided Q means Q equals some lambda P. So the some multiples of this lambda P or some rational multiple lambda P which lies in where? Which lies in set T. Since here lambda G fall in set T, so lambda P also fall in set T, means what is Q? Since P and Q are monic polynomials, surely this lambda is 1, so P equals Q. But what's our requirement? P equals Q, where Q be a monic polynomial in set T, so clearly P be a minimal polynomial of alpha over Q, hence this alpha is an algebraic integer. Okay, alpha is not, so it is, the minimal polynomial over Q has coefficient in set. Why? Because P equals Q. What is Q? Q be a monic polynomial having coefficient in set, and P be the minimal polynomial of alpha over Q. But here we prove that P equals Q, hence P be a polynomial having integer coefficients. Okay.